Alright guys, continuing with our lecture of stereochemistry, alright, in the same chapters 3 and 4, there's a term called chirality. Now what chirality means is if I have molecules, okay, or a molecule I should say, and I draw the mirror image of said molecule, sometimes the molecules could be superimposable on one another, and sometimes they can't be. Molecules that are identical but not superimposable by their mirror images are known as chiral compounds. So, hands, for instance, all right, our right and left hand, we have 5 fingers on each hand. If we look at it and we look at the mirror image, no matter what I do, I can't make them superimposable on one another. Therefore, our hands would be known as a chiral compound or chiral hands. All right, so if I have a compound and its mirror image is not superimposable, then I'm said to be a chiral compound. If my mirror images are superimposable on each other, then they are said to be achiral. A coming from like absent, without. A meaning without. Without chirality. Socks would be a good example, and the slide uses the socks also, would be a good example of something that's achiral. There is no left and right sock. Okay, so your socks are superimposable. The mirror image can fold out or flip over and line up perfectly and look identical. Therefore, socks are achiral. So molecules could be chiral or achiral. All it means is my mirror image of said molecule superimposable? Okay. So, let's say you have to do this on an exam, or you have to do this for a problem for the SATs, the MCATs, all right, or the GREs or something like that. All right. Draw your molecule first and use the dash wedge method. So let's take a look at the whiteboard here, and we're going to use the dashboard, and I'll use the same one that they use on the slide. What did they use here? 1, 2, 3. So they use 2-butanol to do it, and that's the classic one that's used to show all of this going on. All right, so the first thing to do is draw your carbon, okay, like so. That has the 4 different groups on it. So in 2-butanol, there's a methyl group up here. Now we have to draw it in the stick and wedge form. So draw something coming out of the board, draw something going in. Usually when you're doing this, you draw the wedge here and the dash here, but it really doesn't matter. I get into the habit of putting the hydrogen on the dash, and then over here would be your CH2, CH3. Just so you see it, here's how you would have drawn it linear, right? You would have did if we do the line method, you would have did this. All right, there's our CH3, here's our CH2, here's our CH with our OH on it, here is our CH3. Okay, we're drawing this carbon, blowing it up. Now, this carbon here, this one right here, is known as a stereogenic carbon. And what stereogenic means is I'm bonded to 4 different things. Okay? 4 different things. Now here's where you're, if you bought your molecular model kits or you have one, these could come in real good handy. Real good handy. I don't think that's proper English. But they can become really handy or a really good thing to have. All right. For you to see these if you have a tough time. And when I was in Ergo, I had a tough time seeing 3D. So the model kits helped me. But this would not be a stereogenic center because it's bonded to 3 hydrogens, so not 4 different things. Same here, 2 hydrogens, same there. So that's the only stereogenic carbon. Now sometimes people use stereogenic and chirality interchangeably. And some books do, some lectures online do. They're not the same thing. One goes with the other. I need a stereogenic center to show chirality, but just because I'm a stereogenic center doesn't mean I'm chiral. Okay? So I need a stereogenic center to be chiral, but, just because I have a stereogenic center doesn't mean I'm a chiral carbon. Chiral means mirror image is not superimposable. Stereogenic means I'm just bonded to 4 different things. So we draw in our fake mirror, and then we draw in the mirror image. And to draw the mirror image, you're basically copying what you see here, except it's whatever's back here is still back here. That's still on the top. The H is still here. Right? And then the OH is right there. Now, no matter what I do, and this is why it's important to have 3D, because this is coming out of the board at you, all right, and this is going backwards. So you have the carbon, you have something in the plane, you have something coming out, you have something going back. Well, no matter what I do to turn this, so I got to line these up, right, if they're going to be superimposable. If I go to flip this and put this on here, what happens to that OH? Okay, so I'm going to do what? I'm going to flip this way. I'm going to turn it this way. The OH goes from, so I'm going to do 2 turns. That's how you have to see this. So the CH2 to come over here, right, is going to turn and point out, and then turn and come over like this. That means this is going to go into the board on that turn, or be, this is going to be parallel with the carbon, parallel with the board on the first turn, when this is pointing out. And then the OH is going to be going backwards, all right, when I complete it. So I can never line these up because this OH will be coming out, and this one, when I go to line it up, will be going backwards. And again, if you can't see it, and you don't have a model kit, toothpicks and marshmallows work, toothpicks and, sticks and whatever to see it. Because, again, here's what would happen. This is in the board, okay? I would turn it once to come out, and then I would turn it to there, so this would line up. Perfect. However, the OH is coming out. So first turn would be this. Next turn would be going backwards into the board. Okay? Hopefully you could see that. So, the mirror images of 2-butanol, as we have it drawn here, are not superimposable. If my mirror images aren't superimposable, we say that it's a chiral carbon, so that carbon that I start is a chiral carbon. It's a stereogenic center. And the mirror images that are not superimposable, and here's another definition, an important definition, because you're going to see this over and over again. Right here, they are called enantiomers. You might hear someone get real fancy and call them enantiomers. All right, enantiomers works for me. An enantiomer is a mirror image of a molecule, or mirror images of a molecule that are not superimposable. So in order to have those, you need a chiral carbon, and in order to have a chiral carbon, you need a stereogenic center. Okay. All right, next. Here we go. So what do the stereogenic centers have to do with it? All right, here we go. If there's no stereogenic center, no carbon that's bonded to 4 different things, there will be no, the chances are the molecule is achiral. There's always exceptions to every rule out there, but for the most part, if I don't have a stereogenic center, I'm not going to be a chiral center, and the compound won't be chiral. Therefore, the mirror images will be superimposable. Therefore, there will be no enantiomers. So let's put that all together. No stereogenic center, so no carbon with bonding to 4 different things. Most likely then, my molecule will not be chiral, which means my mirror image will be, so not chiral means achiral. My mirror image will be superimposable, which means we won't have any enantiomers. If I have only one stereogenic center, then our molecule will always be chiral. The mirror images will always not be superimposable. The mirror images will be enantiomers of one another. If we have two or more stereogenic centers, I could be chiral, I cannot be chiral. It all depends. I'd have to actually draw out my mirror images and take a look. If I want to narrow it down even before looking at just the stereogenic centers, let's say we look at the stereogenic centers. We have multiple. I want to know if it's achiral or chiral without drawing out the mirror image. Well, I can look at it, and if my molecule contains a plane of symmetry, meaning I could cut it in half equally, okay, that means probably I'm an achiral compound. If I don't have a plane of symmetry, then I'm probably a chiral compound. So achiral mirror images are superimposable. Chiral compounds, they are not. Chiral compounds will lead to enantiomers. Okay. So here they're showing the plane of symmetry, the idea. First thing, okay? Right away, they're showing the plane of symmetry. There is a plane of symmetry, so this is going to be achiral, this is going to be chiral, with no plane of symmetry. However, we didn't even have to do the plane of symmetry because we can look. Carbon is bonded to two hydrogens here, and two different things. So it's only bonded to three different things. It does not have a stereogenic center. So most likely it was going to be achiral to begin with. And now I see that there's a plane of symmetry. I most likely, almost now, definitely I'm achiral. Here, bonded to four different things. So I have a stereogenic center. And again, organic chemists usually use a star to, or an asterisk to signify the stereogenic center. I'm bonded to four different things. No matter which way I cut this, okay, up, down, however, I can't get a plane of symmetry. I'm probably going to have an enantiomer. I have a chiral compound. Okay. So there's another way of drawing things known as Fisher projections. Fisher projections take what you see on the left-hand side, the wedge dash form, and turn it in, but it's only used for stereogenic centers. Okay? Only used for stereogenic centers. With the Fisher projection, you essentially draw a cross. The middle is your stereogenic center. On it goes your elements. Okay? Whatever they are. We'll stick with the butanol, and they give you a different example on the slides, but that's fine. Okay, we'll stick with the butanol. All right. So we'll say, all right, we'll go CH3 is here. Let's say CH2, CH3 is down here. OH is here, and H is over here. Just for OH and H. What the Fisher projection shows for a stereogenic center is really this. Here's your carbon. This is coming out at me. This is also coming out at me. This is going backwards. And this is going backwards. Now, I went to Catholic school my whole life. Well, for 13 years, from kindergarten through high school. So in high school chemistry class, when we were learning Fisher projections, they said, Jesus is coming off the cross to hug you. I mean, it's been in my head since, 1998 and stuck there. So, but whatever's on the T is coming out at us, and whatever's on the top is going backwards. All right, it's just a way of showing stereogenic centers. And we could see that on the PowerPoint, what they did here. All right, with our compound here, we have a stereogenic center. All right, right here. These two are going back and these two are coming off. And as it says hugging up here. Most of the book says the horizontal are hugging you. And like I said in Catholic school, Jesus was hugging you in organic chemistry, all right? Okay. So everything has a mirror image, unless you're a vampire molecule, which we aren't. All right. The question is, are the mirror images superimposable or not? If the molecule and its mirror image are not superimposable, we say it's chiral. All right. So we're talking about the terms that we're just reviewing them here. And then stereogenic centers determine chiral. All right. But don't use them interchangeably, even though books like to, presentations like to, papers like to. They're not indistinct. You need stereogenic centers to be chiral, usually, but just because I'm a stereogenic center doesn't mean I'm a chiral center. Okay. All right. So stereogenic centers, again, you're looking for things that are bonded to four different things. Four different things here. But they're both carbons. No, this is an ethyl chain. This is a propyl chain, a bromine, and a hydrogen. Four different things. Your sp hybridized carbons are not going to be, all right, because they're going to be triply bonded to something. sp2 hybridization, they're going to be double bonded to something. So the first thing you want to look for is any sp3s. And you want to remove any CH2 groups and any CH3 groups. So I'm looking for stereogenic centers. Okay. So here they go with their 2-butanol again. Showing that we have our enantiomers. Okay. And I explained, use your dots, dash and wedges. And as you use your dash and wedges, God, my voice tonight is just awful. As you use your dash and wedges, all right, make sure you put one molecule on the dash, one on a wedge, and two in the plane. Okay, that's going to be very important. So we have our enantiomers drawn. All right. Okay, now, how do we tell the difference? Because they're both 2-butanol. No matter how I look at this, they are both 2-butanol. The difference is their orientation in space, and we have to distinguish that orientation in space. Because if we don't distinguish that orientation in space, then this whole mirror image and enantiomer stuff is useless, and there is a difference. Okay? So, and I don't have a handout on the Kahn-Ingold prelogue. We looked at it in the last thing, but this was openware slides, so I'm using them. They were there. We're going to arrange things by atomic number. Highest atomic number gets the highest number. Okay? In priority. Here's the deal. I cannot stress this enough. Hydrogen, the lowest atomic number, which is usually hydrogen, but the lowest atomic number to apply these rules has to be drawn to the back. Take a note on that on this slide or wherever you're taking your notes. When we're going to prioritize the functional groups attached to a stereogenic center, the lowest atomic number has to be drawn to the back. You have to turn it to the back. If you don't, you are going to prioritize wrong, and your R and S, which we'll talk about, notations are going to be off. Okay, so we look at these, and if we go by numbers, now it just so happens these are all drawn in the plane, so we don't have to worry about putting hydrogen in the back. However, for our intents and purposes right now, highest atomic number is bromine, then chlorine, then fluorine, then hydrogen. Bromine, number 1, then chlorine, then fluorine, then hydrogen. We are going this way with priority. We are going clockwise. All right, clockwise tells us this is, and that is terrible, this is R. R to the right, S to the left, counterclockwise is S. So, let's take a look. And we already went through all of this when we were doing E and Z, so I'm going to skip ahead. All right, and they're doing the same thing. Hey, a double bond counts as 2 oxygens. If you need to review it, go ahead. But let's look at this right here. Okay, where did hydrogen go? Why is hydrogen not here? What's going on? Again, you have to take this molecule and put the hydrogen towards the back. So, let's see if we did this one right. Let's go back a few slides and see if we did this one right. If I put hydrogen to the back, right? So this is all in the plane. If I put hydrogen to the back, what's going to happen? So to flip this, I'm going to put hydrogen to the back, so I'm going to actually turn this upwards, so chlorine's coming out at me. We're still going 1, 2, 3 this way. We're still going right, and we should be okay there to put hydrogen to the back. Okay? So let's look at the one we just saw here. Yep, too far. There we are. Okay, get rid of hydrogen. Put it to the back. Okay, so we're going to have to rotate it a little bit to get rid of it. But we're still 1, 2, 3. And that's an S. Okay, because 1, 2, 3, we're going left. And that's S configuration. So we would say, name the compound, and put an S in parentheses out front. Okay, so each stereogenic center has to be signified with R and S. Okay. Each one has to be designated R and S, and it helps a lot if you just assign your hydrogens towards the back right away. If not, you're going to have to rotate and twist. So when I ask it on an exam, let's say next Thursday, a week today, or if you guys decide you want it on Wednesday, whatever it is. Okay. Make sure you draw hydrogen towards the back and not just assign the chip rules and move on. So this one has 2 stereogenic centers. It is 2,3-dibromopentane, but we need 2s3r because it's saying the second carbon has S configuration while the third carbon has R configuration. Okay, so let's go back to our 2 enantiomers of butanol. Let's look at these 2 right here and see, are they R, are they S? What's going on? First thing I look at, hydrogen's in the back. Good. Which has the highest priority, highest atomic number? Oxygen, oxygen. Then an ethyl group wins the war, and then here. And now, 1, 2, 3, we're going to go this way. This is the S form, S2-butanol. And this is the R form, R2-butanol. Okay? But please, 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 I know it's like the 10th time I'm saying it within the last 3 minutes, make sure hydrogen goes to the back. All right? And that's what they're showing you here. Make sure hydrogen goes to the back. What are you seeing? Make sure the fourth one's in the back. And if it's not hydrogen, let's say that was a chlorine, then my methyl group is my lowest. Whatever your lowest atomic number is, goes to the back. Okay, R and S isomers. Enantiomer A, R-butanol. Enantiomer B, S-butanol. Okay. All right, so depending on how many stereogenic centers I have will determine how many stereoisomers I have. The formula is 2 to the n, where n is the stereogenic centers. So if I have one stereogenic center, I have 2 stereoisomers, which will end up being enantiomers of one another. If I have 2, I should have 4. Okay. If I have 0, I have 1, and it doesn't mean I have one isomer, it just means I have one molecule. So 0 stereogenic centers, won't be chiral, so on and so forth. Okay. So we look at the 2,3-dibromopentane. Okay. 2 stereogenic centers here and here. Okay. So first step, to draw all 4 out. Number 1, draw the mirror image. Just like I showed you on the board, what's coming towards me stays coming towards me, what's going away goes away. Draw your mirror image, and that's what they did here. So these are non-superimposable. All right, so these are enantiomers of one another. And you can assign R and S as a practice for you. Like here's functional group number 1. Here's number 2, here's number 3. Hydrogen's in the back. Save yourself time. Always put hydrogen in the back if you are given the option. So that's going this way, counterclockwise. That's S. 1. Okay. Now we come over here to this one. All right, and we say, all right, I got bromine. Then I go through this carbon with all the junk on it, and then the ethyl group. So this one's R. So this is S. This is R. All right, but they're enantiomers of one another. I stopped writing enantiomers there. All right. So that's 2 of our 4, because we have 2 stereogenic centers, 2 to the n, 2 squared is 4. How do I get the next ones? Okay, here's what you do. Take your original compound. Okay, so here's our original that we drew out, that was there, that we drew the mirror image of. And just change one of these. Okay, just change one of those. So this is showing how you get the enantiomers. And then we are going to look at right here. Here's our original compound. Switch one of them. It doesn't matter. You want to switch these 2, or do you want to switch these 2? Doesn't matter. They pick these 2. Take whatever was on the wedge, put it on the dash. Okay? These 2 are related to each other. They're stereoisomers that are not mirror images. Stereoisomers that are not mirror images are known as diastereomers. Okay? So there's our 3rd one. To get our 4th one, then draw the mirror image of each other. So these 2 are diastereomers of one another. These 2 are enantiomers of one another. And there are your 4. So draw your molecule, draw the mirror image. Take your original molecule and flip one of the wedges with the dashes. You have diastereomers. And then draw a mirror image of that new stereoisomer. Okay, so if we were summing this up, I think they do it on this next slide. Yes, they do. A and B to one another are enantiomers. So here's the 4 stereoisomers of our molecule here, of 2,3-dibromopentane. A and B are enantiomers. C and D are enantiomers. A to C is a diastereomer. A to D is a diastereomer. B to C is a diastereomer. B to D is a diastereomer. Enantiomers, mirror images that are not superimposable. Diastereomers, isomers that are not mirror images of each other. Stereoisomers that are not mirror images. This would have an RS notation. This would have an RS. This would have an RS. This would have an RS. Okay. Now we get into something that's a little funky called the meso compound, and it's interesting. So let's just work this one out. We have, instead of 2,3-dibromopentane, we have 2,3-dibromobutane. All right, so it shows us that we have 2 stereogenic centers. 2 to the n tells us we should have 4 stereoisomers. So let's go and try to draw out the 4 stereoisomers. Okay, I draw my carbons, I have my wedge, I have my dash, I draw the mirror image, it's not superimposable, boom, we have our enantiomers. All right, we got our 2. So then you say to yourself, well, we just did this. So now I'm just going to switch one of these wedges with one of the dashes. Okay, so let's do that. We'll switch one of the wedges with one of the dashes. Boom, boom. We have our diastereomer to one another. And put diastereomer. Okay, so there's number 3. So we have A, we have B, we have C. And then our last step was draw the mirror image of that new compound. The problem is, if you draw the mirror image of this new compound, they're identical. They're the same thing. So even though the math says we should have 4 stereoisomers, we really only have 3, because the mirror image of our third one is an identical compound. If the compound, all right, has a stereogenic center, but the mirror image makes it achiral, we call it a meso compound. So a meso compound is an achiral compound that contains a stereogenic center when it should be chiral, but the mirror image ends up being superimposable, so therefore it's achiral. Okay. I could tell if it's a meso compound, and here's where, if you go back to your slide, 0 stereogenic centers, most likely achiral. 1, always chiral. 2 or more could be could be chiral or could be achiral. Well, we looked at 2 stereogenic centers with the 2,3-dibromopentane that was chiral. Now we're looking at 2 stereogenic centers that's not. And we can go back to that line of symmetry to predict if I'd have a meso compound or not. If you're having a tough time with the terms, slow the video down, pause it, start making definitions in your notebook or on the slides, however you're comfortable doing it. Okay. So enantiomers to one another, diastereomers to one another, and this thing, because its mirror image is identical, is known as a meso compound. All right. So if you're in lab, and depending on where you have lab, they might have something to measure optical activity. And all optical activity is, all right, the machine is called a polarimeter. And what it does is, how does it act in polarized light? And when light comes from a source, it spreads out all over. What a polarimeter does is make it line up in a single plane. And you could see there's a measurement as you put your sample in, as the light passes through. Does it rotate to the right? Does it rotate to the left? It has nothing to do with R and S. It has nothing to do with assigning R and S, okay? Nothing to do with that. But here's exactly what it is. A light source, the polarimeter will make the light source, instead of spreading all over, all in one direction. If it doesn't move it, we say it's optically inactive. It's just a way to determine and distinguish. But what it could do, as you can see, it could start rotating light in a specific direction, left or right. Okay. If I rotate it to the right, all right, dextrorotary means to the right, D or a plus symbol. If I rotate it to the left, you'll see an L or a negative. Okay. Again, no relationship between R and S. Now, let's say I had R, butanol, 2-butanol and S2-butanol. Okay, I have enantiomers of one another. If I put the enantiomer R in, it'll rotate the light a certain number of degrees in one direction. If I put S in, it'll do it the same number of degrees in the opposite direction. If I have a complete 50-50 mixture of both enantiomers, the light won't rotate at all because the one enantiomer will be rotating it so many degrees to the right, but the other one will be rotating it so many degrees to the left, and it won't cause anything to happen. And that's what this is indicating here. If I were to take R-butanol versus, if I were to take two enantiomers of one another, let's just say that, an R and S enantiomer of one another, and try to tell which one's which. If I measure their melting points, they're going to be identical. If I measure their boiling points, they're going to be identical. The only thing that's going to be different is their optical rotation. The degrees will be the same, but one will be to the right and one will be to the left. Okay. If I put a mixture, however, this is what's very interesting. If I mixed up my enantiomers, okay, in a 50-50, a 60-40, whatever it is, if I mix them up, it could change the melting point and the boiling point if it is a mixture. And if it's a complete 50-50 mixture of enantiomers, the degrees of rotation will be 0. A mixture of enantiomers is known as a racemic mixture or racemate. Racemic mixture. Okay. So that ends chapter 4, guys. Okay. So your next exam will be on essentially stereochemistry. All right, everything that we did in these slides. You know, and the thing is too, nomenclature doesn't go away. Everything we've done doesn't go away, so you might see that still sprinkled in because, hey, is this R or this is S? Name this compound. Okay, 2-butanol. Now I named it 2-butanol, but now I have to put R and S. I have to put all those toppings on there. Okay, so you should be able to do cis-trans. You should be able to do RS. All right, you should be do everything in this, and that's what our exam will be on, stereochemistry and chirality. Okay, and then we'll talk on Tuesday when you want to have that next exam, because we only have 2 weeks left. All right, guys, if you have any issues or problems, all right, let me know over the weekend. If not, I'll talk to you on Tuesday.